Let's begin. But before we journey across billions of years, let's start with just 1 second, right here, right now. I want you to listen, just listen. Don't try to hear anything, just be aware of the sounds that are and the sounds that aren't. What do you hear? The quiet hum of a computer, the distant sound of traffic, the ticking of a clock. Now, try to listen between those sounds. Listen to the silence in your apartment, the stillness of the room you're in. It's a quiet, heavy, peaceful kind of nothing. It feels stable. It feels permanent. Now let's take that feeling and expand it. Imagine a quiet so profound it's not just the absence of sound, but the absence of anything that could make a sound. Imagine the deep, cold stillness of the space between planets, or the immense dark void between galaxies. This is the silence of the cosmos, an empty stage waiting for the play to begin. Our story starts here in this concept of nothingness, but it's a nothingness that is almost impossible for us to truly grasp. We all ask the question, what happened before the Big Bang? It's a human question. We think in terms of cause and effect of yesterday and tomorrow. But before is a word that describes time, and the Big Bang is the event that started time. So asking what came before the Big Bang is like asking what is north of the North Pole. The question itself doesn't quite fit. We aren't talking about a Monday that came before a Tuesday. We're talking about a state of existence or non-existence where our rules of physics, our understanding of time, of space, of cause and effect completely dissolve. It's not a place or a moment. It's a state of pure unimaginable potential where the laws of our universe had not yet been written. So where was everything? Where were all the stars, all the galaxies? Where was the carbon that makes up your body, the iron in your blood, the calcium in your bones? Where was all of it? The mathematics, the deepest theories of our physics all point to one baffling answer. It was all contained in a single point. I want you to really try and picture this. Don't think of a dot like the period at the end of this sentence. Don't even think of a grain of sand. Think of a point of zero size, a point that is infinitely small, infinitely dense, and infinitely hot. We have a name for this, a singularity. It's a word we use when our mathematics break. It's the universe's way of telling us that our understanding has hit a wall. But the concept is staggering. Everything we see, every one of the 2 trillion galaxies we've estimated, each containing hundreds of billions of stars, all of it, all the matter, all the energy, all of space itself was compressed into a single mathematical point of no dimension. It was a universe of pure unified potential waiting for the first word, and then that word was spoken. We call it the Big Bang. But this name is one of the most misleading names in all of science. It creates an image of a bomb, an explosion, a piece of cosmic shrapnel flying out from a central point into a dark, empty room. That is not what happened. It was not an explosion in space, it was the expansion of space itself. There was no outside for it to explode into. There was no center for it to explode from. The singularity wasn't in the universe. The singularity was of the universe. And then it began to grow. A better way to picture it is to imagine a tiny microscopic balloon with dots drawn all over its surface. As you inflate the balloon, the surface itself stretches. The dots move away from each other, not because they are sliding across the balloon, but because the rubber between them is expanding. This is what happened. Space itself began to unfurl. Time began to flow. In the very first, tiniest fraction of a second, a slice of time so small our minds cannot comprehend it. The universe swelled from a point smaller than an atom to the size of a grapefruit, and it kept going, expanding faster than the speed of light. This was inflation. It was the universe taking its first deep breath. So what would you have seen in those first moments? Nothing. You would have seen nothing. Not because it was dark, but because it was blindingly, overpoweringly bright. In the first few minutes, the universe was not stars and galaxies. It was a soup. A perfectly uniform, searingly hot, chaotic soup of pure energy and the most basic fundamental particles. It was millions of degrees. It was so hot and so dense that atoms as we know them couldn't hold together. Everything was a swarm of loose subatomic parts. And it was opaque. It was an impenetrable fog. Light itself, the particles we call photons, could not travel. As soon as a photon was created, it would immediately slam into another particle, be absorbed and be spat out in a random direction, only to hit another particle and another. It was a universal whiteout. If you could somehow exist in that early universe, it would be like being inside the very core of a star or trapped in the thickest, most absolute fog imaginable. A blinding, searing, uniform glow with nowhere for the light to go. This was the universe's infancy. A hot, cloudy, chaotic nursery filled with the raw ingredients of everything to come. It was a state of perfect blazing uniformity, but hidden within that uniformity, tiny microscopic whispers of imperfection were already there, seeds that would over eons grow into everything we know. For the first few 100,000 years, the universe was a paradox. It was full of light, but it was completely opaque. Imagine being trapped inside the heart of a star, or perhaps inside the thickest, densest fog you can possibly imagine. A fog not of water, but of energies and charged particles. The cosmos was a blistering, hot, pressurized soup of plasma. Photons, the very particles of light, were constantly being created. But they couldn't travel. They would take one step only to immediately slam into a free-roaming electron getting absorbed and scattered in a random direction. There was light, yes, but there was no view. There was no far away. The universe was a blinding, impenetrable wall of its own energy. But all this time, the universe was doing the one thing it does best. It was expanding. And as it expanded, it cooled. The relentless expansion gave everything more room, and the intense, frantic energy began to settle down. It was stretching, cooling, relaxing, until it reached a magic number, a tipping point. This happened when the universe was about 380,000 years old. The temperature finally dropped enough for things to find a partner. The frantic for his electrons slowed down just enough to be captured by the waiting protons. In that moment, they recombined. They held hands. They balanced each other out, and the first stable neutral atoms were born. Simple hydrogen. And the effect was instantaneous. Everywhere all at once the fog lifted. The electrons which had been the source of the fog were now safely locked away in atoms. The light particles, the photons that had been trapped and bounced around for millennia were suddenly free. They were released. They began a journey travelling in perfectly straight lines through a newly transparent universe. This moment, this is the first light. It's the oldest light we can ever see. It's the earliest possible photograph of the cosmos. And we can still see it. When we build special telescopes that look for microwaves, we can see this ancient light approaching us from every direction in the sky. It has travelled for nearly 14 billion years to reach us. The expansion of the universe has stretched it out during its long journey, changing it from a brilliant visible glow into a cold, faint, invisible microwave hum. Call it the cosmic microwave background. It is the afterglow of creation, the baby picture of the universe showing us what it looked like the very moment it became clear. But here is the beautiful, strange part of the story. The moment the universe became transparent, it also went dark. The initial blazing light of the Big Bang was now free to travel, but it was fading, stretching, cooling, and nothing had replaced it. The lights went out. This next great chapter is called fittingly the Dark Ages. It lasted for hundreds of millions of years. Imagine an emptiness and a silence so profound it stretches over eons. The universe was filled with enormous drifting clouds of neutral hydrogen and helium gas. No stars, no galaxies, no planets, no light, just an expanding, cooling, patient darkness. The stage was set, the raw materials, the atoms were there, but the play had not yet begun. The universe was just waiting, but it wasn't truly idle. There is a force that never sleeps, a gentle, persistent whisper that works tirelessly in the dark gravity. In this immense dark ocean of gas, some places were just slightly denser than others, by pure chance, and where there was slightly more stuff, gravity's whisper was slightly louder. Come here, it said. And slowly, patiently, over millions and millions of years, that whisper pulled the gas clouds together. Tiny drifts became large clouds. Large clouds became massive swirling reservoirs of hydrogen. And as gravity pulled them tighter and tighter, the pressure and the temperature at the very center of these collapsing clouds began to skyrocket. Finally, after perhaps 100 or 200 million years of absolute darkness, the first lights in the universe flickered on. The first stars were born. These were not stars like our sun. These were the pioneers. We call them Population 3 stars. They were forged from only the materials the Big Bang provided, pure hydrogen and helium. Because they lacked all the other elements we know, there was nothing to stop them from growing to truly monstrous sizes. We believe they were hundreds of times more massive than our own sun. And because they were so massive, they burned with an intensity we can barely comprehend. They were dazzling, brilliant blue-white giants burning through their fuel at an incredible rate. They didn't just light up the darkness, they shattered it. But a life lived so intensely cannot last long. Our sun has a lifespan of about 10 billion years. These giants, they were lucky if they lasted 2 or 3 million. They were a cosmic flash in the pan, and their deaths were as spectacular as their lives. When they ran out of fuel, they didn't just fade away, they collapsed under their own unimaginable gravity and then exploded in the first supernovas the universe had ever seen. These explosions were cataclysmic, ripping the stars apart with unbelievable force. But inside that violence, something magical was happening: creation. You see, the Big Bang only made the simplest ingredients. It made hydrogen and helium. It didn't make the carbon that forms the basis of your cells. It didn't make the oxygen you're breathing right now. It didn't make the calcium in your bones or the iron in your blood. All of that, all the stuff that makes us, was forged for the very first time in the dying fiery hearts of these giant stars. They were the universe's first factories. In their final moments, they cooked the hydrogen and helium into carbon, nitrogen, oxygen, silicon, iron, all the way down the table of elements. And when they exploded, they seeded the cosmos. They blasted this new enriched material, this star ash, out into the surrounding gas clouds. We are made from the remnants of those first stars. We are built from their ashes. The Dark Ages were over. The first light had returned. And now, for the very first time, the universe had the ingredients it needed to build something new. It had the ingredients for planets, for complexity, and eventually for us. If the first stars were the first lonely lanterns lit in an infinite darkness, the next question is, why there? Why did those first lights turn on in those specific locations? The universe in its first few million years was remarkably uniform, just a smooth, thin fog of hydrogen and helium. Why wasn't it all just a boring, even fog forever? It's because the fog we could see was not the only thing present. The universe had a secret, a hidden architecture, a silent, invisible majority. We have spent our entire history looking at the light, the stars, the glowing nebulas, the brilliant galaxies, but we've slowly realized that all of that, everything we can see, everything we are made of, is just a tiny fraction of what exists. It's like seeing the foam on the waves, but not the ocean underneath. The vast majority of matter in our universe, about 85% of it, is something else entirely. It is something we call dark matter. It's dark, not because it is black, but because it is completely, totally invisible. It does not interact with light in any way. It doesn't shine, it doesn't reflect, it doesn't even cast a shadow. Light passes right through it as if it weren't there at all. It doesn't interact with normal matter, the atoms that make you and me, except in one crucial way: gravity. Dark matter is heavy, it has the mass, and its gravity dominates the cosmos. From the very beginning, this dark matter was not perfectly smooth. Tiny microscopic variations in density were stretched by the expansion of the universe. Where there was slightly more dark matter, gravity pulled in more. The rich got richer. Over hundreds of millions of years, this invisible material was pulled by its own gravity into an unimaginable structure, the largest structure in existence. It's called the cosmic web. I want you to imagine a spider's web stretched across an entire forest. Now imagine that web fills all of known space. It is a vast three-dimensional lattice. It is made of enormous long strands or filaments of dark matter stretching for hundreds of millions of light years. These filaments connect to each other at nodes, which are dense, heavy intersections where the most dark matter is gathered. And between these filaments and nodes are the voids, vast empty regions where there is almost nothing at all. This web is the skeleton of the universe. It is the invisible scaffolding that was in place long before the first stars ever formed. Now picture the normal matter, the hydrogen and helium gas left over from the Big Bang. This normal gas is the visible stuff, the stuff that will one day become stars and planets. This gas also feels gravity, and the gravity it feels most strongly is from the cosmic web. The web acts like a system of gravitational rivers. The normal gas, like water, flows into these invisible riverbeds. It streams along the enormous dark matter filaments, a slow-motion migration across millions of years. This gas flows and flows and flows, all heading toward the densest parts of the web, those heavy nodes. What happens when you funnel massive amounts of gas into one location? It gets crowded. The gas piles up, swirling and compressing within these deep gravitational wells of dark matter. As the gas cloud gets denser, it begins to collapse under its own gravity. And just as we saw before, when a gas cloud collapses, it forms stars. But this time, it's not just one star or a small cluster. This is a cloud containing the mass of millions or billions of suns, all held together in one place by the immense invisible anchor of the dark matter node. These were the first galaxies. They were not the beautiful grand spirals we see in pictures today. No, these first proto-galaxies were small, messy, chaotic swarms of stars. They were dwarf galaxies, but they were intensely bright, churning with the fires of millions of massive hot blue stars, which lived fast and died young in spectacular supernova explosions. These were the first small towns, the first bright neighborhoods built at the intersections of the cosmic highway. But the universe was much smaller then. and these new galaxies were much closer together. And they were all still moving, still flowing along the filaments of the web, still being pulled by gravity. This began the era of mergers. For the next several billion years, the universe was a construction site. These small dwarf galaxies racing through space were constantly running into each other. When two galaxies collide, it isn't like a car crash. The stars themselves are too far apart to ever hit each other. Instead, it is a magnificent slow-motion gravitational dance that can take 500 million years to complete. As two galaxies approach their dark matter, halos merge first, gravity reaches out and they pull on each other, distorting their shapes, pulling out long tidal tails of stars and gas. They pass through each other, but their combined gravity is too strong for them to escape. They slow down, reverse course, and fall back toward each other. They might pass through each other several times, and each time their gas clouds smash together, triggering a furious storm of new star formation lighting up the merging galaxies. Eventually, this chaotic dance ends. The two galaxies settle their stars, mingling their gas clouds, mixing. They become one single larger galaxy. This is how galaxies grow. It is a process of cosmic cannibalism of small systems merging to build giant ones. Our own Milky Way is a product of this. Deep within our galaxy are ancient stars that were born in smaller dwarf galaxies, galaxies that we ate billions of years ago. Even today, we are in the process of pulling apart and consuming smaller galaxies that have strayed too close. This slow, patient assembly, guided by an invisible hand, built the cosmic cities we see today. The majestic spiral galaxies, the enormous glowing elliptical galaxies, each one is a metropolis, built from the bricks of smaller galaxies, all constructed at the intersections of that vast dark cosmic web. And inside these new growing cities, the universe was becoming more interesting. The elements forged in the hearts of the first stars, the carbon, the oxygen, the iron, were now being mixed and recycled into new generations of stars. The chemical complexity of the universe was growing. The stage was being set for something new, for planets, for worlds. After looking out at that endless dark ocean, at those trillions of islands of light we call galaxies, let's turn our gaze back to our own. Our island, our home port in the cosmic sea. We call it the Milky Way. On a clear dark night, far away from the glare of city lights, you can see it. It's not a single point of light like a star nor a small disk like a planet. It looks like a faint shimmering cloud, a beautiful spilled band of light that stretches across the entire sky. For thousands of years, people looked up at this celestial river and told stories. The ancient Greeks thought it was the milk of a goddess. The Romans called it the Via Lactea, the Milky Road. They were right. It is a road. It is our home. And we are not looking at it, we are looking through it. If we could take a spaceship and travel impossibly fast, leaving our galaxy far behind, and then turn around to look back, what would we see? We would see one of the most magnificent sights in the universe. We would see a vast spinning disk of light. Imagine a cosmic pinwheel 100,000 light years across. But it's not just a simple spiral. In the very middle, we wouldn't see a small round ball of stars. We would see a thick, bright, glowing bar of stars. It's a dense, yellowish-white bar packed with billions of older stable stars. And from the very ends of this enormous bar, the great arms spiral outwards. These arms are bluer, hazier, and filled with gas and dust. This is where the action is. This is where new stars are being born right now, illuminating the gas clouds around them. Because of this structure, the central bar and the arms that spring from it we call our home, a barred spiral galaxy. It's a swirling, majestic city of stars turning slowly in the silence of space, and we are on one of its endless journeys. Let's take a trip. Let's fly from our vantage point far above the disk and head straight for that bright central bar. The closer we get, the more crowded it becomes. The stars are packed together, here millions of them, in a space where out here we would only find a few. They are moving incredibly fast, orbiting something unseen. The light from this core is intense, a blinding fog of starlight. It is a place of chaos and breathtaking beauty. Right at the very, very center, the mathematical heart of our galaxy, lies a monster. But it's our monster. We give it a name from our star chart, Sagittarius A star. It is a supermassive black hole. The words super and massive barely do it justice. This single object, this thing, has the same mass as 4 million of our suns. 4 million stars like our own, all crushed down by gravity into a single invisible point. We can't see it, of course. A black hole is a place where gravity has become so powerful that nothing, not even light itself, can escape. It is a hole in the fabric of space. We only know it's there because we can watch the stars right next to it. We can see them whipping around this invisible point, moving at millions of miles per hour like water swirling down a drain. It's a place of incredible violence and power, but it is also the anchor. It is the immense gravitational anchor that holds our entire galaxy of stars together. It is the engine at the heart of our home, but we don't live there. We aren't anywhere near that beautiful, terrible, chaotic center. If the Milky Way were a giant spinning city, we would not be living downtown. We would be far, far out in the quiet suburbs. Our Sun, our Earth, and all the other planets in our solar system are nestled in one of the smaller partial spiral arms. We call it the Orion Arm, or sometimes the Orion Spur. It's a relatively quiet, peaceful neighborhood, and that it turns out is a very, very good thing for us. Down in the center, or even in the main busy spiral arms, things are dangerous. Stars are much closer together. The radiation from the central black hole and all those crowded stars is intense. And worse stars are exploding all the time. These supernova explosions are the most powerful events in the universe, and they sterilize everything for light years around them. Life, especially complex life like us, would have a very hard time getting started, let alone surviving for billions of years. But out here, it's peaceful, we have space, we have quiet, we are far enough away from the dangerous radiation of the core. We are not too close to any big unstable stars that might explode. It's the perfect place for life to take its time to evolve over billions of years, to grow from simple cells into thinking, feeling beings who can look up and wonder where they are. Scientists have a name for this perfect cosmic real estate. They call it the Galactic Habitable Zone. It's just like the Goldilocks zone we talk about for planets not too hot, not too cold, but just right for liquid water. This is the same idea, but for the whole galaxy. If you are too close to the center, it is too dangerous, too much radiation, too many explosions. But if you go too far out, way out to the very edges of the galaxy, there's a different problem. There isn't enough stuff. The elements we are made of, the carbon in our bodies, the oxygen we breathe, the iron in our blood, these things were not made in the Big Bang. They were cooked inside the hearts of giant stars and then spread across the galaxy when those stars exploded. Out in the distant fringes, there haven't been enough generations of stars to create and spread these heavy elements. You can't build rocky planets like Earth. You can't build life. But here in our Orion Arm, it is just right. We have enough heavy elements to build our world and our bodies, but we are far enough away from the dangerous core to be safe. We are living in the galactic sweet spot. So we are in this safe suburban arm in our sweet spot. But let's pull back again. Let's see the whole thing one more time. How big is this home of ours? Our galaxy, the Milky Way, is about 100,000 light years from one side to the other. 100,000. That number is so big our minds just can't hold it. Remember, a light year is the distance light travels in 1 year. Light is the fastest thing that exists. It travels at 186,000 miles per second. Even at that impossible speed, a beam of light would take 100,000 years just to cross from one edge of our galaxy to the other. Our entire solar system, which seems so vast to us, is just a microscopic speck of dust in this structure. And this structure our Milky Way contains, well, we don't know for sure. Our best guess is somewhere between 100 billion and 400 billion stars. Let's just say 200 billion to be modest. 200 billion suns. Many of them, perhaps most of them, have planets of their own. It makes you feel two things at the exact same time, doesn't it? First, it makes you feel impossibly wonderfully large. We are not separate from this, we are this. The atoms in your body, the iron in your blood, the calcium in your bones were all forged in the hearts of stars that exploded long ago, right here in this galaxy. We are the children of the Milky Way. We are the universe becoming aware of itself. We are part of this grand spinning living city of light. And then at the very same second, it makes you feel incredibly profoundly small. We are just one species on one tiny blue planet orbiting one very average yellow star tucked away in a quiet corner of just one galaxy among trillions. This is our home, this grand, beautiful, spinning island in the dark, our island of light, the Milky Way, and for so much of this journey we have kept our gaze focused inward. We have looked into the heart of our own Milky Way, traced its spiral arms, and wondered at the darkness that holds its center. It is our home, our island in the great cosmic ocean, but the universe does not end at the border of our city of stars. The void between the galaxies is vast, an expanse of quiet so profound it's almost impossible to comprehend. But it is not empty, there are other islands. If you go out on a perfectly clear dark night, far from the polluting glow of city lights, and you look up toward the constellation that bears her name, you might see it. You must let your eyes adjust. You are not looking for a pinpoint of light like a star. You are looking for a smudge, a tiny, faint, fuzzy patch of light like a forgotten cloud. That smudge is perhaps the most profound object you can ever see with your unaided eyes. It is not a cloud of gas. It is not a distant star cluster within our own galaxy. It is something else entirely. For centuries we called it the Andromeda Nebula, believing it was just another local curiosity. It took one man in the 1920s to shatter our understanding of home forever. That man was Edwin Hubble. Using the most powerful telescope of his time, the giant Hooker telescope on Mount Wilson in California, he stared at this fuzzy patch. He was looking for a specific type of star, a Cepheid variable, which pulses with a reliable clockwork rhythm. He found one, and then another. These special stars are like cosmic measuring sticks. Because we know their true brightness, we can tell how far away they are just by seeing how faint they appear to us. Hubble did the math, and the answer he found was staggering. This nebula was not thousands of light years away, it was millions. It was so far away it could not possibly be part of the Milky Way. In that single brilliant moment of calculation, the known universe exploded. Our Milky Way was not the entire cosmos. It was just one island universe, and that faint fuzzy smudge was another, an equal, a neighbour. We now know this neighbour as the Andromedae galaxy, or Messier 31. It is our closest major sibling, a massive spiral galaxy, very much like our own, but slightly larger. While we have perhaps 200 or 300 billion stars, Andromeda boasts a trillion. It's a true heavyweight, and it's located about 2.5 million light years away. The faint light you see on that dark night, that light has been travelling for 2.5 million years to reach your eyes. It left Andromeda long before modern humans ever walked the Earth. Andromeda and our Milky Way are not alone. We are the two dominant members of a small gravitationally bound family of galaxies known as the Local Group. It's our galactic county. This family includes the two of us, another smaller spiral galaxy called Triangulum, and dozens, perhaps 50 or 60 of smaller dwarf galaxies. These little galaxies are like gravitational pets, small ancient clusters of stars that are caught in the orbit of the larger galaxies. We are all bound together, drifting through the intergalactic void as a single connected family. But there is something unique about our relationship with our biggest neighbour. When astronomers look out at the distant universe, they see that almost every other galaxy is rushing away from us. Their light is stretched into longer, redder wavelengths, a redshift, which is the telltale sign of the universe's expansion. But Andromeda is different. When we look at Andromeda, its light is not stretched. It is compressed. It is blue-shifted. This means one simple, terrifying and beautiful thing: it is not moving away. It is coming straight for us. Across the vast emptiness of 2.5 million light years, the gentle, relentless force of gravity is pulling our two great galaxies together. We are falling toward each other. The speed is almost incomprehensible, about 110 kilometers or 70 miles every single second. This is not a maybe, it is a certainty. Our galaxy is on a collision course. Now the word collision brings to mind a violent destructive crash, an explosion of fire and chaos. But this will be something else entirely. You must remember the most important thing about a galaxy. It is mostly empty space. The stars themselves are tiny isolated pinpricks separated by trillions of miles of nothing. When the Milky Way and Andromeda merge, it is almost a statistical certainty that not a single star will actually collide with another star. Our sun will not crash into an Andromedan sun. The solar systems will sail right past each other like ghosts passing in the night. It will not be an explosion, it will be a dance. This grand cosmic merger is scheduled to begin in about 4.5 billion years. As the two galaxies draw near, their mutual gravity will begin to wreak havoc. Our beautiful orderly spiral arms will be pulled, twisted and torn apart. The same will happen to Andromeda. Long spectacular streamers of stars and gas called tidal tails will be flung out into the void. The two galaxies will pass through each other. The stars will sail past, but gravity will have taken hold. They will slow down, stop, and then fall back together again. They will pass through each other a second, and perhaps a third time, each pass mixing them more thoroughly, like stirring cream into coffee. Over hundreds of millions of years, this dance will continue. The two supermassive black holes at the heart of each galaxy will find each other. They will begin their own ferocious dance, spiraling closer and closer until they merge into one truly colossal black hole. And the gas. The vast clouds of hydrogen and helium, which are the stellar nurseries of both galaxies, will collide. This will trigger a spectacular burst of creativity. A starburst. The merging galaxies will light up with the fire of trillions of new stars being born all at once. If any conscious beings are still here on this planet orbiting a much older, larger red giant sun, the night sky will be a sight beyond our wildest dreams. It will be a blaze of glory. The familiar constellations will be gone, replaced by a sky filled with chaotic streams of stars and blazing new nebulae. After this dance is complete, the two spirals will be gone. In their place will be a new single gigantic galaxy. We call this future home Milkomeda. It will likely be a giant elliptical galaxy, a vast globe-shaped city of stars glowing with the combined light of two galactic families now one. It is a profound reminder. In the universe, nothing is static, nothing is permanent. Even the great galaxies, the island universes that seem so eternal, are on a journey. They are born, they live, they dance, and they merge. Now let's pull our view back. We've been talking about stars and planets, the small intimate details of the cosmos. But where do all these stars live? They live in cities. Immense spinning glowing cities of stars, gas and dust all held together by gravity. We call them galaxies, and if we are to understand the universe, we must understand these grand structures. Welcome to the Galactic Zoo. Let's start with the one we know best, our own home type, the spiral galaxy. When you think of a galaxy, this is probably what you picture. They are the beautiful, vibrant pinwheels of the cosmos. Our Milky Way is one. The Andromeda Galaxy, our closest large neighbour, is another. What makes them spiral? It's a combination of gravity and rotation. At the centre of most large spirals is a bright, dense cluster of stars called the central bulge. This area is mostly full of older yellowish stars, and at the very heart of that bulge we usually find a supermassive black hole, a gravitational monster that holds the whole structure together. Flowing out from this centre are the arms. These arms are not solid. You can think of them as cosmic traffic jams. They are density waves, areas where gravity has slightly compressed the gas and dust. As clouds of hydrogen gas drift into these arms, they get squeezed. This squeezing is the trigger. It's what sparks the birth of new stars. This is why the spiral arms are so bright and often look blue. They are filled with massive, young, hot-burning blue stars. These arms are the stellar nurseries, the creative rivers of the galaxy. We live in one of those arms. Our Sun is just one of hundreds of billions of stars orbiting the centre of the Milky Way, taking about 230 million years to make a single trip around. But not all galaxies are like ours. Let's look at the next enclosure in the zoo, the elliptical galaxies. If spirals are the vibrant, bustling cities of creation, ellipticals are the ancient, sprawling continents. They are settled. They don't have the beautiful, flat, spinning disk. They don't have the arms. Instead, they are massive, three-dimensional blobs shaped like an egg or a football. Some are nearly round, while others are long and stretched. And their colour is different too. They glow with a soft reddish-yellow light. This colour tells us their history. They are made almost entirely of very old stars. There is very little gas or dust left in them. Because they lack this raw fuel, star formation has almost completely stopped. They are red and dead, as astronomers sometimes say. They are quiet cities where the lights are on but no new building is happening. But don't let their quiet nature fool you. They are often the largest and most massive galaxies in the universe. Some, like the giant M87, are home to trillions of stars compared to our Milky Way's few hundred billion. They are the true heavyweights. And how did they get so big? They are cosmic cannibals. Elliptical galaxies are the end product of massive collisions. When two or more spiral galaxies like our own crash into each other over billions of years, their beautiful, delicate structures are completely destroyed. The stars, gas and dust are all thrown together, eventually settling into one enormous, disordered elliptical shape. Next we find the irregular galaxies. These are the rebels, the beautiful chaos of the cosmos. As their name suggests, they have no defined shape at all. They are not neat spirals, they are not smooth ellipticals. They are messy, scattered, and often stunningly beautiful. What makes them this way? Often they are the victims of gravitational bullying. They are smaller galaxies that have passed too close to a much larger neighbour. The immense gravity of the larger galaxy pulls on them, stretching them like taffy and tearing them apart. Our own Milky Way has two small irregular galaxies orbiting it, visible from the southern hemisphere, the Large and Small Magellanic Clouds. They are our cosmic companions, but we are slowly pulling them apart. This gravitational tug-of-war can have a spectacular side effect. As the gas inside the irregular galaxy is squeezed and pulled, it can trigger an incredible frantic burst of star formation. They light up with activity, a chaotic flurry of creation, even as they are being destroyed. Finally, there is a fourth main type, a sort of in-between category, the lenticular galaxies. The word lenticular just means lens-shaped. These are a hybrid. They are like a spiral galaxy that has lost its way. They have the flat spinning disk. They have the central bulge, but they have no spiral arms. Why? Because like the ellipticals, they have used up almost all of their free gas and dust. There's no fuel left to create the bright blue stars that light up the arms. They are the ghosts of spirals. They have the structure, but the engine of creation has shut down. They are a common step in the life of a galaxy, a transition phase between the energetic spiral and the quiet elliptical. This brings us to the most important rule of the Galactic Zoo. The exhibits are not static. Galaxies are living, changing, evolving things. The universe is the dynamic dance floor, and the dance is driven by gravity. Galaxies are constantly interacting. They pull on each other. They steal gas from one another. They sideswipe each other. And very often they collide head-on. A galaxy collision is one of the most spectacular events in the universe, a process that takes hundreds of millions of years. When two galaxies collide, the stars themselves almost never hit each other. The space between stars is just too vast. An individual star would fly right through the other galaxy without ever noticing. But the gas and dust, that's a different story. The massive clouds of gas from each galaxy slam into each other, creating shock waves that compress the gas and trigger a starburst, a galaxy-wide firestorm of new star formation. And the gravity of the two galaxies pulls and twists their shapes, flinging out long, beautiful tidal tails of stars and gas into empty space. Over billions of years, the two will dance around each other, merge and finally settle into a single massive and often elliptical galaxy. This is not just something that happens to other galaxies, it is our future. Our Milky Way is hurtling toward the Andromeda Galaxy at over 200,000 miles per hour. In about 4.5 billion years, our two great spiral galaxies will begin their collision. The night sky for any life that exists then will be a spectacular, terrifying and beautiful sight. The two galaxies will merge, and our distant descendants, if they exist, will live in a new giant elliptical galaxy. The zoo is alive. The shapes we see are just a snapshot in time, a single frame in a movie that has been playing for nearly 14 billion years. Let's pause for a moment and think about the centres of galaxies. In our own Milky Way, the heart of our galaxy is a relatively calm place. There is a giant black hole there. Yes, we call it Sagittarius A star, but it is a sleeping giant. It sits in the dark, quietly sipping on the occasional wisp of gas. The stars around it orbit in peace. But the universe wasn't always this quiet, and not all galaxies are as peaceful as ours. In the vast cosmic library, there are entries that speak of a violence so extreme it rewrites the very definition of energy. There are places in the cosmos where the centre of a galaxy is not a quiet harbour, but a raging cosmic furnace. We call these active galactic nuclei, a simple, almost boring term for the most powerful sustained phenomena in the universe. It means quite literally that the nucleus, the core of the galaxy, is active. And when this core awakens, it doesn't just whisper, it screams. The most spectacular, the most luminous, the most terrifyingly powerful of all these active centres are the quasars. The word quasar is short for quasi-stellar radio source. When astronomers first detected them in the 1950s and 60s, they were a complete mystery. They looked like single faint stars, but they were blasting out incredible amounts of radio waves unlike any normal star. And when we measured their distance, the puzzle deepened. They were not stars in our own galaxy. They were impossibly far away, billions of light years. So what is a quasar? It is the grand, terrible performance of a supermassive black hole in the act of eating. Imagine the scene. In the centre of a young, chaotic galaxy, a black hole of unimaginable mass, perhaps 1 billion times the mass of our Sun, sits at the centre of a cosmic feast. Huge, swirling clouds of gas and dust, and even entire stars, are pulled in by its gravity. But they don't just fall straight in. Like water spiralling down a drain, this material forms a vast, flat, rotating structure called an accretion disk. This disk is the engine of the quasar. It is here that the light is born. As the matter in the disk spirals closer and closer to the black hole, it moves at fractions of the speed of light. The friction, the pressure, and the intense magnetic fields in this swirling vortex heat the material to millions of degrees. It is a storm of superheated plasma glowing with a brightness that defies comprehension. It is not the black hole itself that shines. A black hole by its very nature is a trap for light. It is the process of feeding it. It is the dying scream of matter converted into pure energy just moments before it crosses the event horizon and disappears from our universe forever. The power of this process is difficult to put into words. A single active quasar can outshine its entire host galaxy. Think about that for a second. A galaxy like our Milky Way contains hundreds of billions of stars all shining at once. A quasar driven by a region of space that might only be the size of our solar system produces more light than all of those billions of stars combined. It is a single point of light that burns brighter than 1,000,000,000,000 suns. It is a cosmic blowtorch, a beacon that is visible across the entire observable universe. And this is perhaps their most important role for us as observers, because they are so bright we can see them from incredibly far away. And in astronomy, far away is the same as long ago. When we look for quasars, we don't find them in our local cosmic neighbourhood. The galaxies near us are old and stable. Their black holes have eaten all the nearby gas. Their feasts are long over. Instead, we find quasars billions of light years distant. We see them shining at us from a time when the universe was young, when galaxies were first forming and colliding, and when vast reserves of hydrogen gas were still available to fuel these central monsters. The quasars are beacons of the void in the most literal sense. They are lighthouses shining from the distant past. The light from the most distant quasars we can detect has travelled for over 13 billion years to reach our telescopes. We are seeing light that was emitted when the universe was less than 1/10 of its current age, a cosmic infant. They are a direct window into the fiery, chaotic adolescence of the cosmos. But they are not just passive beacons, they are not just cosmic artifacts. We have come to understand that quasars are a fundamental part of galactic evolution. They are not just in their galaxies, they shape their galaxies. This idea is called AGN feedback. As the quasar blazes its intense radiation and the powerful jets of particles it often shoots out at near the speed of light act like a cosmic hurricane. This outpouring of energy heats up the gas in the surrounding galaxy. It creates a powerful wind that can blow the galaxy's supply of cold gas, the raw fuel for star formation, clean out of the galaxy itself. A quasar, in its ferocious act of feeding, effectively shuts down the ability of its host galaxy to create new stars. It is a cosmic thermostat. The black hole grows, it turns on. As a quasar, it blasts its surroundings, it cuts off its own food supply, and the galaxy settles down. The quasar fades and the galaxy's wild star-forming youth comes to an end. It matures into a stable, quiet galaxy much like the one we live in. It's a beautiful, violent cycle of self-regulation. The very monster at the heart of the galaxy is what dictates the galaxy's fate. When we look at these distant, brilliant points of light, we are seeing the ghosts of this ancient, formative violence. They are the engines that forged the universe we know today. They are a reminder that the deep, peaceful quiet of our own night sky is a silence that was earned a calm that followed a storm of unimaginable and truly cosmic proportions. And yet for all our searching, for all our mapping of the skies, we held on to one fundamental, comfortable assumption, that the universe was stable. We assumed it was a static, unchanging, eternal stage on which the dramas of stars and planets played out. We thought it was the firmament, something solid and fixed. This assumption was perhaps the single most profound mistake in the history of astronomy. And the first crack in that comfortable idea came not from a grand theory, but from a quiet, tedious observation. It began with an astronomer named Vesto Slipher. In the 19-teens, he wasn't looking for cosmic revolution. He was just doing his job, pointing a telescope at those fuzzy, swirling patches of light we called spiral nebulae. We didn't even know they were galaxies yet. Many thought they were just gas clouds inside our own Milky Way. Slipher's task was to analyse their light to see what they were made of. He used a spectroscope, a tool that splits light into its rainbow of component colours like a prism. But when you do this to a star or a galaxy, you also see dark lines, a kind of barcode that tells you exactly what chemicals are present. Slipher found those barcodes, but he found something else, something deeply weird. To understand it, you have to think about sound. You know the sound of an ambulance siren as it approaches you. It's high-pitched. Eee. Then as it passes you and moves away, the pitch drops. Ooh. That changes the Doppler effect. The sound waves get stretched out as the source moves away. Light does the exact same thing. Light from an object moving toward us gets compressed, shifting its barcode toward the blue end of the spectrum. Light from an object moving away from us gets stretched, shifting its barcode toward the red end. We call this redshift. Vesto Slipher looked at the barcodes of his spiral nebulae, and almost every single one he measured was redshifted. They weren't just drifting around randomly. Overwhelmingly, they were moving away from us. And not just drifting, they were fleeing some at speeds of millions of miles per hour. It was a baffling discovery. Why was the universe running away from us? For a while, the data just sat there. It was a puzzle with no picture on the box. Then came Edwin Hubble. Hubble, working in the 1920s, had a new, more powerful telescope, and he had a secret weapon, a new way to measure the distance to these nebulae. He proved first that they weren't gas clouds in our backyard. They were island universes, galaxies in their own right, millions of light years away. But he didn't stop there. He took his distances and compared them to Slipher's redshifts. He plotted them on a graph, and in that graph the entire cosmos snapped into focus. What he found was a straight line, a stunning, perfect relationship. A galaxy that was, say, 10 million light years away was moving away from us at a certain speed. But a galaxy that was 20 million light years away, twice the distance, was moving away at twice the speed. A galaxy 30 million light years away was moving at 3 times the speed. This became known as Hubble's law. The farther away a galaxy is, the faster it is receding from us. Now, the first very human impulse is to feel a little special. Everything is moving away from us. Does that mean we're at the center of it all, the very center of a great cosmic explosion? It's a logical thought, and it is completely wrong. The truth is so much stranger and so much more profound. The best way to picture what's happening is the famous raisin bread analogy. Imagine you are a baker with a very large lump of raisin bread dough. You are yourself standing on one specific raisin inside that dough. You look at the raisin closest to you 1 inch away. You see another raisin farther away, maybe 4 inches away. Now you put the bread in the oven. The dough begins to rise. The dough itself expands uniformly in every direction. After an hour, you look again from your home raisin. The raisin that was 1 inch away is now 2 inches away. It has moved 1 inch away from you, but the raisin that was 4 inches away is now 8 inches away. It has moved 4 inches away from you. From your point of view, the farther raisin appeared to move faster. But were the raisins flying through the dough? No. The dough, the space between them was expanding, carrying the raisins along for the ride. And here's the most important part. If you were standing on any other raisin in that loaf, you would see the exact same thing. Every raisin would see all other raisins moving away from it, with the most distant ones moving the fastest. There is no center, or if you prefer, every place is the center. We are the raisins. The galaxies are the raisins. And the dough is the fabric of space-time itself. This is the great expansion. It's not that galaxies are flying through space away from a central point. It is space itself that is stretching. The light from those distant galaxies is redshifted because the very space it has been traveling through for billions of years has been expanding underneath it, stretching the light waves as they travel. This discovery, this simple line on a graph, transformed humanity's understanding of our home. The universe was not a static, eternal state. It was a dynamic, evolving, growing thing. And if it is growing, if it is expanding today, well, that implies something profound about yesterday. If we are all moving apart, it means that in the past we must have been closer together. If you run the movie of the universe backward, winding back the clock on this great expansion, all the galaxies rush back toward each other. The space between them shrinks, the universe gets denser, it gets hotter. Keep rewinding, past the formation of the first stars, past the first atoms, keep rewinding all the way back. Edwin Hubble's discovery, Vesto Slipher's observation. It was the first observational proof that our universe was not eternal, at least not in this state. It was the first concrete evidence that our entire cosmos, had a beginning. As we sit here contemplating the vastness of the universe, it's easy to feel a sense of accomplishment. We've decoded the light from distant stars, we've uncovered the birth of the cosmos in a great expansion, and we've even glimpsed the invisible laws of gravity that bend space-time itself. It feels like we've assembled a beautiful, intricate puzzle. But what if I told you that the pieces we've assembled, every star, every planet, every nebula, every human being, are only the decorative border of that puzzle? What if the real picture, the vast center, is still completely blank, hidden from our view? This isn't a philosophical riddle, this is the reality of modern cosmology. Our journey has now brought us to the edge of what we know, and we are staring into the two greatest mysteries of our time. We call them dark, not because they are evil, but because they are invisible to all our instruments. Let's start with the first mystery. For decades we thought we understood how galaxies worked. We look at our own solar system and it behaves perfectly. The planets closest to the Sun, like Mercury, move very fast in their orbits. The planets far away, like Neptune, move very slowly. This makes perfect sense. Gravity is strongest near the centre of the Sun, and it gets weaker the farther out you go. Less gravity means a slower orbit. We assume naturally that galaxies would work the same way. The center of a spiral galaxy is a huge bright bulge of billions of stars. We expected the stars on the very outer edges of that galaxy, far from the gravitational center, to be moving slowly crawling along in their orbits. In the 1970s, an astronomer named Vera Rubin decided to test this. She wasn't looking to start a revolution, she was just doing careful methodical science. She measured the speed of these outer stars in neighbouring galaxies like Andromeda. What she found was impossible. The stars on the outer edges were not moving slowly. They were moving incredibly fast. They were moving so fast that the gravity from all the visible matter in the galaxy, all the stars, gas and dust we could see, should not have been strong enough to hold on to them. By all our calculations, these fast-moving stars should have been flung off into the darkness of intergalactic space millions of years ago. The galaxies should have torn themselves apart, and yet they don't. The galaxies are still, the stars are still there, held in a perfect spinning disk. The conclusion was unavoidable, and it was staggering. There must be more gravity, and if there is more gravity, there must be more stuff. A lot more. There must be a huge invisible halo of something surrounding these galaxies, holding them together with its immense gravitational pull. We call this invisible substance dark matter. We know it's there. We can map it by seeing how its gravity bends the light from distant objects like a cosmic magnifying glass. But we have no idea what it is. It is not just faint stars or cold gas. It doesn't interact with light or matter in any way we recognize. It seems to be a new kind of particle, something entirely outside our current understanding of physics. Billions of these particles are likely passing through your body through this very room right now, as if you weren't even there. This invisible matter isn't just a minor addition, it's the skeleton of the cosmos. It seems that this dark matter formed a vast invisible web throughout the early universe and the normal matter. We see the stuff that makes galaxies simply fell into these massive pre-existing gravitational pockets. Without dark matter, it's possible that none of us would be here. For a while, this was the biggest mystery, but in the 1990s we found something even stranger. Astronomers had a simple, long-standing question: what is the ultimate fate of the universe? We knew the universe was expanding from the Big Bang, but we also knew that gravity pulls everything back together. It was a cosmic tug-of-war. We assumed one of two things would happen. Either gravity would eventually win and the expansion would slow down, stop and reverse, collapsing the universe into a big crunch. Or the expansion would just barely win, slowing down over trillions of years until the universe was a cold, dark and empty place, the Big Freeze. In 1998, two separate teams of scientists set out to measure exactly how much the expansion was slowing down. They used distant exploding stars called supernovae as standard candles to measure distances across the universe. They checked their data. They rechecked it. They thought their equipment was broken because the data showed the impossible again. The expansion of the universe is not slowing down. It is speeding up. Think about that. It's as if you threw a ball into the air and instead of it slowing down from gravity, it suddenly accelerated, shooting away from you faster and faster into the sky. Some anti-gravity force must be at work pushing the very fabric of space-time apart. This force, whatever it is, seems to get stronger as the universe gets bigger. We have absolutely no idea what it is, we simply call it dark energy. So let us take a final inventory, Utora. Let's make a complete list of everything that makes up our universe based on all our best measurements. First, there is the normal matter. This is everything you've ever seen, touched, or imagined. It is the Earth, the Sun, every star in the Milky Way, and every other galaxy in the observable universe. All of it. That normal matter makes up just 5% of the total universe. Then there is the invisible scaffold, the dark matter that holds our galaxies together. That accounts for about 27%, and the rest, the mysterious unknown force pushing everything apart, that dark energy makes up 68% of all reality. This is the state of our knowledge. We have spent millennia looking up at the sky, and we have only just realized that we do not understand 95% of what we are looking at. We are in a very real sense strangers in our own cosmos. This is not a failure. It is the very definition of scientific humility. It is the universe reminding us that we have only just begun our journey. The greatest discoveries, the most profound truths about the nature of reality are still out there waiting in the dark. As we drift through this understanding of the cosmos, from the smallest quantum vibrations to the grandest clusters of galaxies, we have built a picture of a universe that is vast, ancient, and filled with potential. We've seen how physics and chemistry through fire and ice can give rise to the complex molecules needed for life. We've looked at the billions of stars in our own galaxy, and the billions of galaxies beyond that. We've learned that planets are not rare, They are common orbiting countless suns. Many of them are in the Goldilocks zone, just the right distance for liquid water to exist, for the gentle chemistry of life to begin. Our galaxy alone is estimated to have billions of planets that could in theory support life, and our galaxy is one of billions. Our universe has had over 13 billion years for this story to play out, not just once, but over and over again. And so we arrive at a quiet, deeply unsettling question. A question first famously asked by the physicist Enrico Fermi during a casual lunch. Where is everybody? This is the heart of what we call the Fermi paradox, or the Great Silence. The numbers are overwhelming. The statistics scream that the sky should be teeming with life, that we should be surrounded by signals, by artifacts, by the comings and goings of civilizations far older and more advanced than our own. And yet when we listen, there is nothing. When we look, we see only the silent, beautiful, unfeeling light of stars and gas. The universe is profoundly, deeply quiet. This silence forces us to think, to wonder, and to propose ideas that are as fascinating as they are at times frightening. Perhaps there is something we call a great filter, a barrier that is incredibly difficult for life to overcome. This filter could be anywhere in the long chain of development. Maybe the filter is behind us. Maybe the initial spark of life, the jump from non-living chemistry to a simple reproducing cell, is the miracle. Maybe it happened only once here on Earth. Or perhaps the jump to complex multicellular life like animals and plants is the real hurdle. If that's the case, we are the lucky ones. We made it through. But there is a more sobering possibility. What if the great filter is ahead of us? What if every intelligent civilization, upon discovering a certain level of technology like nuclear power or global-scale industry, inevitably destroys itself? What if the universe is full of the ruins of civilizations that flared brightly for a few thousand years before winking out, unable to manage their own success? In this case, the silence is a warning. Or perhaps the answer is simpler. Perhaps our Earth is just that special. This is the rare Earth hypothesis. Maybe the recipe for complex life isn't just liquid water and a good star. Maybe you also need a large moon exactly like ours to stabilize the planet's tilt and create tides. Maybe you need a giant planet like Jupiter perfectly placed to act as a cosmic shield sweeping up dangerous asteroids and comets. Maybe you need plate tectonics, the slow movement of continents, to regulate the climate over billions of years. Perhaps the combination of all these factors is so incredibly rare that we are effectively the only ones. There are other less lonely ideas. Maybe we are just the first. Someone has to be. Perhaps the universe has only recently cooled and settled enough for life like us to emerge. We could be the early ones, waking up in a cosmos that is still young, and it will be our descendants who one day greet the next civilizations to be born. And then there are the more exotic possibilities. What if they are hiding? Some call this the zoo hypothesis, that advanced civilizations are watching us like we watch animals in a nature preserve, bound by a rule not to interfere with our natural development. Or a darker version, the dark forest hypothesis, which suggests that the universe is a dangerous place. The smart thing to do is stay quiet, because any signal you send out could attract a predator. In this scenario, the silence is not emptiness, it's fear. This question, are we alone, is perhaps the most profound question we can ask. The answer, whatever it is, will change humanity forever. Think about it. If we find life, even simple microbial life, trapped in the ice of a distant moon or in the sands of Mars, it would be the greatest discovery in history. It would tell us that life is not a miracle unique to Earth. It would mean the universe is alive, the filter is likely behind us, we are not alone, the stars would look different, suddenly filled with promise, with neighbours we have yet to meet. And what if we find nothing? What if for centuries to come, as our telescopes get stronger, and our reach extends farther, we find only emptiness, only dust and ice and silent rock? What if it is truly just us? This in its own way is just as profound. It places a different kind of weight on our shoulders. If we are the only consciousness, the only thinking, feeling beings in this entire galaxy, then we are the only ones who can appreciate all this. We are the universe's way of knowing itself. All the beauty of a nebula, all the power of a star, all the intricate dance of the planets, its meaning exists only in our minds. If we are alone, then our existence is not just a curiosity, it is a responsibility. It means that all of our art, our music, our science, and our compassion, this little spark of awareness, is the most precious and rare thing in the entire cosmos. It means we have a duty to protect it, to cherish it, and to carry that spark with us out into the great silent darkness. The silence of the universe is not an answer. It is a question. It is a mirror reflecting our own hopes, our own fears, and our own place in this grand unfolding story. We are the listeners, and we are just beginning to tune in. Let's take a deep breath. Together, let's just zoom out. Pull your awareness back from this room, from this very moment. Float up past the ceiling, high above your town or city. See the curve of the earth, that thin, fragile line of blue atmosphere that holds all of life. This is our home, this is our stage. But let's keep going. We float past the moon, our silent companion. We see the earth shrink to the size of a marble, a beautiful, swirling orb of blue and white. We pass the orbits of Mars and Jupiter, feeling the immense current pull of our star, the Sun. Our entire solar system, with all its planets and moons and asteroids, is just one small family of objects orbiting a single average star. Now let's pull back even further. Our star is just one of hundreds of billions in a vast spinning city of light. This is our galaxy, the Milky Way. We aren't even downtown. We live out in a quiet suburban neighborhood, a smaller spiral arm known as the Orion Spur. From here, the galactic center is a distant, brilliant glow, a place of unimaginable energy and density that we can only observe from afar. You might think this is the end of the journey, that our galaxy is an island floating alone in the dark, but it's not. The emptiness between galaxies isn't empty at all. Just as stars are grouped into galaxies, galaxies are grouped into, well, groups. Our Milky Way is part of what we call the local group, a small cluster of a few dozen galaxies, including our big neighbor Andromeda. And even this group is not alone. Let's pull back again until our entire Milky Way galaxy is just a single point of light lost in a crowd. We are part of an even grander structure. It's a structure so vast it's difficult to find words for it. Astronomers call it a supercluster. Our home supercluster is named Laniakea. It's a beautiful Hawaiian name that means immense heaven, and it is immense. Laniakea is a sprawling celestial continent home to 100,000 different galaxies. 100,000, each one of them like our own containing hundreds of billions of stars. The scale is simply staggering. All the stars you've ever seen, all the constellations, all the distant nebulae, they're all just a tiny part of one neighborhood in this one supercluster. But here is where the perspective truly shifts. This supercluster, this immense heaven, is not static. It is not just sitting there. It is moving. Everything within it, including our own local group, including our Milky Way, including our solar system, we are all moving together in a single unified direction. We are not just drifting, we are part of a flow. Imagine a vast cosmic river miles wide and impossibly deep. The galaxies are not like boats sitting on the water. They are the water. We are all part of a single massive current, a river of galaxies all being pulled through space at an incredible speed over 2 million kilometers per hour. We are flowing towards something. Out there in the distance, hidden from our direct view by the dust and stars of our own galaxy, lies an anomaly. It's a point in space with such a massive gravitational pull that it is slowly, patiently reeling in everything for hundreds of millions of light years around. We don't know exactly what it is. We can't see it directly. We only know it's there because of the effect it has on us and on all the thousands of galaxies around us. We call it very simply the Great Attractor. We are part of a grand pilgrimage, a flow of 100,000 galaxies all streaming toward this one mysterious unseen gravitational basin. Now think back to that image of Earth, that pale blue dot, as the great astronomer Carl Sagan called it. He spoke of it as a mote of dust suspended in a sunbeam. He was right. But now we see that this mote of dust is not just suspended, it is going somewhere. Our entire planet, our entire history, all the wars and all the love, all the art and all the tragedy. It is all happening on a tiny speck of dust that is itself caught in a cosmic river flowing with 100,000 other galaxies toward an unknown destination. It can make you feel small, unimaginably small. Just one person on one planet in one solar system in one arm of one galaxy in a cluster of galaxies all flowing as one part of a supercluster pulled by a force we barely understand. If you were looking for a definition of insignificant, that might be it. But let's hold that thought. There is another way to see it. Yes, we are physically tiny. Yes, we are made of the same stuff as the stars and the dust between them, mostly hydrogen, carbon, oxygen. We are a collection of stardust. But we are a very special collection of stardust. We are the part of the universe that woke up. We are matter that has, through billions of years of cosmic and biological evolution, become organized in such a complex way that it can think, it can feel, it can wonder. We are the universe becoming self-aware. We are not separate from this grand cosmic flow. We are the flow. We are a tiny, intricate eddy in that giant river. But we are the eddy that has developed the capacity to look back at the river itself. We are the part that can measure its speed. We are the part that can map its currents and give names to its destinations like Laniakea and the Great Attractor. We are the universe's way of knowing itself. So when you look up at the night sky, you're not just an observer looking at the cosmos. You are the cosmos looking at itself. The atoms in your brain that are processing that light, that are feeling that sense of awe. Those atoms were forged in the hearts of stars that died long ago. Our place in the flow is this strange, beautiful paradox. We are at the same time completely insignificant and profoundly significant. We are a speck of dust, and we are the mind that understands the dust. We are a passenger on a journey we cannot control, and we are the cartographer drawing the map of that journey. We are quite simply the universe's consciousness, and our purpose, if we have one at all, is to do what we are doing right now, to be still, to be aware, and to wonder. We have travelled so far together. We began in a moment of impossible density and light. We watched the first atoms form. We drifted through the clouds of gas that would become the first stars. We've witnessed the birth of galaxies, the quiet explosion of supernovae, scattering the seeds of life and the unlikely beautiful awakening of consciousness on a small blue world. And now our journey must do what all journeys do. It must face the end. We have spent our time looking back at the billions of years that brought us here. But now we turn our gaze forward into the deep, deep future. What will become of this grand cosmos? The answer, it seems, is in the hands of that quiet, invisible force. We only recently discovered dark energy. This mysterious presence, this gentle but persistent push that is causing space itself to expand, holds the final chapter. It is currently the dominant force in the universe, and it is accelerating our expansion. How this story ends depends entirely on the nature of this energy. Right now, science sees two possible paths leading into the far, far future. The first, and perhaps the most likely, is called the Big Freeze, or more poetically, the heat death of the universe. In this scenario, dark energy continues to push just as it does now at a constant rate. For the next few billion years, not much changes, but the expansion is relentless. The other galaxies, the beautiful spirals and clusters we see in our telescopes, are pushed farther and farther away. They cross a line where the space between us is expanding faster than light itself, and they simply disappear. Their light can no longer reach us. One by one, the distant galaxies wink out of our sky. Our own local group of galaxies will merge into one enormous island, a single vast galaxy alone in an endless empty void. For a time it will be bright, but time is not on its side. The long age of stars, the stelliferous era that we were so lucky to be born into, will come to an end. The universe's supply of gas for making new stars will run out. The existing stars will burn through their fuel. The bright blue-white stars will die quickly. The long-lived stable stars, like our sun, will fade. Finally, even the smallest, dimmest red dwarf stars, the ones that can sip their fuel for trillions of years, will finally go dark. The universe will be left with the corpses of stars. Black holes, cold neutron stars, and black dwarfs. It will become a graveyard of light. And it will get cold. Incredibly profoundly cold as all remaining heat spreads out across the infinite expanding darkness. The universe will approach a state of absolute zero. Even the black holes, the great gravitational engines, will not last forever. Through a process of particle radiation, they will slowly evaporate over timescales so vast they make the current age of the universe seem like a single heartbeat. After all that, what is left? A universe of almost infinite size, dark, empty and cold. A thin, cold soup of stray particles drifting alone in the eternal night. No change, no life, no light, just silence. That is one path, the long, slow, cold fading of the cosmos. But there is another, more dramatic possibility. What if dark energy is not constant? What if it grows stronger over time? This is a theory known as the Big Rip. In this scenario, the expansion of the universe not only continues, it accelerates faster and faster. At first, it looks much like the Big Freeze galaxies fly away from us. But as the dark energy becomes more powerful, its push begins to overwhelm gravity on smaller and smaller scales. A few billion years from now, this phantom energy would be strong enough to tear apart the Milky Way itself, sending all its stars flying into the void. Later it would become strong enough to overcome the gravity, holding solar systems together. Planets would be torn away from their stars. Then as the end approaches, the force would be strong enough to overwhelm the chemical bonds that hold matter. The Earth itself, or whatever is left of it, would be torn apart. In the final moments, this force would become stronger than the forces holding atoms together. The very building blocks of matter would be shredded, and in the final fraction of a second, the fabric of space-time itself would be ripped apart. a final total dissolution of everything, a long contemplative pause, the music swells gently then fades back. These are the endings we can see. One is a slow fade to black, the other is a violent tearing apart, and it is easy hearing this to feel a sense of sadness, of smallness, of cosmic loneliness, a gentle melancholy, the end of everything we have ever known. Oh, absolute. Oh, empty. But I would ask you to hold on to one final thought. The fact that the universe will end does not make it any less beautiful. A sunset is beautiful because it is fleeting. We cherish the cherry blossoms because we know they will not last. The value of this moment is not defined by its permanence. We are alive in the Stelliferous era. We are here in the bright, glorious morning of the cosmos. The universe is still full of light and stars and energy, and the creation of new worlds. We are the children of stardust. We are the universe's own way of waking up and looking at itself. For a brief, brilliant flash of time we exist. We get to look up at the sky and wonder where we came from. We get to learn to feel, to love, and to understand. We are the witnesses. The story of the cosmos from the first light to the final darkness is a grand one, and the miracle, the true unbelievable, breathtaking miracle, is not that the universe will go on forever, but that we were here at all, that we got to open our eyes even for a moment and see the light. Thank you for watching the sky with me. Good night.